Audio quality check. Audio quality check. Audio quality check. So good afternoon to every one of you. Please let me know if the sound quality is fine again today. So if you have any question, please make sure to post them on the live chat. I'll be trying my best to answer all of your questions. And again, all of you know that this is apparently a complicated topic that we're going to discuss today, but I shall try my best to simplify the ideas behind Fourier series so that actually you can understand the underlying idea. And once you understand the underlying idea, I hope you'll be able to solve the complicated problems. So we shall wait for a few more minutes for more people to join, and then we shall start. Again, the video will be available after the stream, and all the handouts and notes will be forwarded to you after the stream. Okay, today we shall actually figure out where the Fourier series actually comes from, and we shall derive the expression for the Fourier series actually, and we shall understand the origin of things in this regard. So I believe this is quite important for anyone to actually grasp the idea, underlying idea, right? If I tell you a formula and ask you to solve a problem, you would be able to solve the problem based on your aptitude, but unfortunately you won't get the underlying idea, right? So in order to have a feeling for it, you have to understand where the things came from, right? So this is what we are going to do today. And again, at the by the end of the class, we shall be solving a few popular problems as well. We shall have some very good quality demos, and we shall see. So let us start our discussion today. And again, we are going to we are starting our discussion on Fourier series and Fourier transform today. This will comprise of 5 total classes. So this is the first one, and this is introduction to Fourier series. So again, the idea of Fourier series is entirely based on the principle of orthogonality of real sinusoids and the principle of superposition. Okay, we shall learn those. But before I can start, let me ask you a simple question. Let me start today's discussion with a very simple question. Okay, I want you to do this integration. This is the definite integral, but I want you to evaluate this. Right. So I want you to calculate this integration where m and n are 2 natural numbers. So that is m and n are something like 1, 2, 3, 4, 5, 6, etc. So I want you to do this integration. All right. So let me proceed with this. Let me do the integration, right? So of course, in this multiplied form, we cannot really do the integration here. So let me just put a half outside, and we'll have this. Right? I don't think there is any problem with this. So with this integration, we already from our 11th standard we know that we can simplify this as this, right? Right? I think that's fine. And with this, we can actually now do the integration, right? So if I integrate cos m minus n t with respect to t, then I would of course have sine m minus n t divided by m minus n minus sine m plus n t divided by m plus n, and the limits are from minus pi to plus pi. So all of you agree to this, right? Again, if you have any question, please post them on the live chat and I'll be trying my best to answer your questions. Right. With that said, what is the result of this integration? What do you think is the result of this integration? Again, recall that we're actually doing this integration, right? Doing this integration, and here m and n are both integers, preferably positive integers for us. Okay, so like 1, 2, 3, 4, etc. And we are doing this integration. Now we are here. We have to put the limits, right? Now do tell me what is the supposed result here. What do you think the answer is, right? Please tell me. Yeah, Obivicious is absolutely correct. The answer is actually 0, right? Why is the answer 0? The answer is 0. Let me say this. But now, before I can explain this to you, recall that recall this, that sine, what is the value of, say, sine pi? What is the value of sine pi? Yeah, all of you know sine pi is 0. What is the value of sine 2 pi? That's also 0, right? What is the value of sine 3 pi? That's also 0. So in fact, sine of n pi is actually 0, right? In fact, that's true for n belonging to any integer, positive, negative, or 0, right? Sine 0 is 0, sine minus pi is 0, sine minus 2 pi is 0, sine pi is 0, sine 2 pi is 0, sine 3 pi is 0, sine any integer pi is 0, right? And because of this, look at this one. What do I have? If I put the upper limit and lower limit, what do I get? If I put the upper limit, what do I get? I get sine, and then this is an integer, and again this is an integer. So if I put the upper limit here, if I put pi here in place of t and also in place of this t, we would end up with integer multiples of pi inside sine, right? Yes, sine and pi equal to 0. So integer multiple of pi inside sine, right? So that way those values will be 0. Again, similarly, when I put the lower limits, those will be again integer multiples of pi. Same thing, like minus pi, minus 2 pi, minus 3 pi, minus 4 pi, and so on, right? So the result is going to be 0, right? So that's simple to understand, I think. So we just said this. We just figured out that this integration we just figured out this. Wait a second. Huh? We figured out that this integration from minus pi to pi on sine mt and sine nt dt is equal to 0, right? We did figure that out, right? But before I can go any further, please tell me, when we are saying this, my question is, are you assuming something? So we have just derived this, but my question is, are you assuming something without telling me? While doing the integration, are you assuming something? Apart from the fact that m and n are both integers, those assumptions are given. But my question is, are you assuming something that you didn't tell me? Yes, m and n are integers. That is already told, right? That is already given. Okay, those assumption is given. So my question is, are you assuming something without telling? So my question is, are you assuming something without telling me, right? Of course, m and n are integers, but did you assume something that you did not tell me? Right? Absolutely, absolutely. That is the correct answer. We did assume, while doing this integration, we did assume something very important. Recall, we just blindly put the upper limits and lower limits, but we did somehow inherently assumed that m is not equal to n. Okay, that was our inherent assumption. Our inherent assumption while getting that 0 as the result of the integration was the fact that we did assume that m is not equal to n. Both of them are integers, of course, but we did assume that they are not equal, because if they are equal, this integration is not valid, right? This integration is not valid if they are equal, right? Because if m and n are equal, then this becomes m minus n becomes a 0. So of course we would have a 0 in the denominator, so that would result into a very weird situation, right? So we did assume that. So let's do the other assumption. Let's say m and n are equal. Let's see what happens then, right? Again, now say m and n are indeed equal, right? And both of them are natural numbers, right? We are assuming natural numbers. We can consider integers as well. Yeah. So in order to get this 0, of course, the assumption is m and n are natural numbers and they are not equal, right? Right. But what if they are equal? What if they are equal? And if they are equal, let's do the integration when they are equal, right? So we are doing this integration again. Sine of mt sine of nt dt, right? And of course, if m and n are equal, then I have this integration as minus pi from pi, and then m and n are equal. We are considering that situation, that particular situation in this regard. So in that situation, what would happen? The value of n and value of n will be equal. So I can put n instead of Obi is partially correct. Let me tell you. We have to put n, say for example, right? So I would now have sine of nt and also sine of nt. So I would have sine square nt, right? Because I just considered m equal to n and I just put I replaced m with n, right? Now of course, again the same thing I can do. I can put a half here and I put a 2 here, and subsequently I have the formula for 2 sine square theta, right? 2 sine square theta is 1 minus cos 2 theta, right? So with that said, I can again write this as integration from minus pi to pi 1 minus cos of 2 nt dt, right? So I can do that. And now if I do the integration, what do I get? I get this. So 1 after integration becomes t, and this one after integration becomes minus sine 2nt divided by 2n, and the lower limit is minus pi and the upper limit is pi, right? Right. Now let's put the upper and lower limits, right? So again, let's see that. So we have half, right? Let's put the upper limit. When I put the upper limit, when pi goes here, okay, in place of t, we are writing pi, of course, that's no problem. But when I put pi here, I again have the same situation. I again have a similar situation, right? We again have a situation where we have a sign of an integer multiple of pi. So when I put pi here, this becomes 0, right? So I have t minus 0. That's for the upper limit. And when I put the lower limit, again in place of t, I put minus pi. So that's the lower limit. And again, when I put minus pi here, same thing happens. We again have an integer multiple of, yes, Akash Kundu is right. The answer would be pi. So if I put minus pi here, so what happens? I subsequently get 0 here, because again that's an integer multiple of pi, right? So I have a 0 here. So if I do the sum here, again the answer is pi, right? So again here we again had an assumption. What assumption did we have? We had this assumption. We had the assumption that m and n are natural numbers and m equal to n, right? M equal to n, right? We did have this assumption, right? So now we can say, we can happily say this, that this is equal to 0 when m not equal to n, and this is equal to pi when m equal to n, and of course m and n are both natural numbers. So is this understood? Because the entire concept of Fourier series actually is based on this. If you understand this well, it will be very easy for you to understand the entire concept behind Fourier series. Please let me know in the live chat if you understand this. This integration, when m and n are integers, can be a 0 or can be a pi result of this integration, depending on whether m is not equal to n or equal to n, right? So all of you, let me know please that whether you understand this or not. All right. So of course, then if you understand this, then of course I can divide everything with pi, and after this line I can very easily modify this and write it as a 1 here and put a 1 by pi here. Is there any confusion with this? So I think it's fine, right? So please let me know if you understand this well. Right. Now let me ask you a simple question then. Imagine I have a signal, right? So imagine now I have a signal xt, okay, and it has it is like this, something like this, say 2 sine t plus 3 sine 2t, right? So Devashish says, please repeat it again for 5 minutes. You can, Devashish, you can always go back in case in the live stream you can always go back. Please watch the video for rewind the video for a few minutes and let me know if you don't understand something from that. Right. Okay, Devashish, please try to follow then. Actually, after the end of the stream, the video will be available on YouTube. So watch that later on. And afterwards, if you have any question after that, please let me know personally through email, and I will answer your questions. Don't worry about that. Okay. So my point so far is that this integration is valid, right? So this results into a 0 when m is not equal to n, and this results into a 1 when m is equal to n, right? So with that said, if I have this signal, right? Say I have this signal and ask you this question. My question is this: I have this signal, and say you only have a waveform. So you don't have an expression for the signal. Imagine this. Imagine you have a waveform for this signal. You don't have an expression for this signal. So you don't really know that the signal is comprising of a sine t with an amplitude of 2 and a sine 2t with an amplitude of 3. You don't know that. Imagine. Okay. You just have the waveform, right? We have the signal. But what if I integrate this signal? What if I multiply the signal? For example, I take xt and multiply it with sine t and integrate it from minus pi to pi with respect to t. Do tell me, what am I supposed to see as the result of this integration? Again, without doing any calculation, what am I supposed to see with this integration? This is the signal, and I don't know what the signal is. Imagine. Okay, but if I can somehow multiply the signal with sine t and do an integration from minus pi to plus pi, what am I supposed to see? Which is 0. Why? Can anybody have some idea? Right, so let me explain. Okay, let me explain this. So what is xt? So now imagine we have xt, right? So what is xt? We know xt, right? So it's 2 sine t plus 3 sine 2t. Yes, you people are partially correct, not entirely. We have this, right? So with that said, can I split this into two parts? Yes, of course. So that would be 2 sine t into sine t dt, and plus, yes, only one of you are correct somehow, and I have 3 sine 2t into sine t dt. So is this line correct? Of course, now try to understand that by virtue of the formula that we discussed just moments ago, for this integration, look at this one. This integration would be a 0 because I have a 2 here and I have a 1 here. I have a 2 here, I have a 1 here. So this integration is 0, right? So these integers do not match. But this is here, m is equal to 1 and n is also equal to 1. For this regard, m was 2, n was 1. So this integration would be 0. But this portion of the integration would not be equal to 0, right? Indeed, this part of the integration would be 2 integration from minus pi to pi sine t dt, and we already know that this portion of the result is actually pi, so the answer is 2 pi, because here look carefully, m and n are equal and both of them are equal to 1 for this portion. So please let me know in the live chat if you understand this. Again, I am going to elaborate on this, so don't worry. So did all of you get this? So I think most of you got this, right? So again, with that said, I have simple questions again. Let me just go back and try to make things slightly more clear for you. Okay, question: what is the integration? What is the value of this? What is this? What is the value of this? What is the value of this? What is the value of this? Yes, of course, here you can see m is equal to 2, and here n is equal to 3. Of course, they aren't equal, so the answer is 0, right? Here also m is equal to 1, n is equal to 3, so they aren't equal, so the answer is 0, right? Right. So minus pi to pi sine 2t dt. What will be the value of this? Again, for this, m is equal to 2 and n is equal to 2, right? So of course this is going to be pi, because both of them are equal, right? Similarly, integration from minus pi to pi sine 3t sine 3t dt, that is also equal to pi, because m is equal to 3, n is equal to 3 here, right? Right. Right. So let me go back and ask you the same question again. So let me ask you again. Say I have a signal which is represented as xt, and it is given as 2 sine t plus 3 sine 2t, right? So if I have a signal like this, then what is the expected result of this integration? Minus pi to pi xt sin t dt. What is the result of this? What is the expected result of this? And what is the expected result of this? So of course I have a 2 sin t component here, and because of that this integration will result into 2 pi, right? So this is going to be 2 pi, and this is going to be, so because we have a 3 here, this is going to be 3 pi, right? Yeah, it's pretty simple to understand, right? Why is the second one 3 pi by 2? Why do you think it's 3 pi by 2? Again, if I simplify the second one, I would have 2 sin t into sin 2t and 3 sin 2t into sin 2t, and for the 3 sin 2t into sin 2t part, I would have 3 into pi. So the answer is 3 pi, right? So please, all of you agree that you follow this, because we are going to proceed from this. So do all of you understand what I just discussed here? If so, then of course I can divide everything with pi. So I can divide everything with pi and put a pi, 1 by pi here, and put a 1 by pi here, right? So it is pretty simple to understand, right? I believe. Not so difficult. But my next question is this: then what is this integration? What is the result of this? What is this integration for the signal? Yes, of course 0, because here look carefully, we have a sin t, of course. So if I multiply the signal with sin t, then I will and integrate from minus pi to pi and divide by pi, I would get a 2. I also have a 2t component, okay, sin 2t component. So again, if I multiply with sin 2t, again I am going to get a value, but I don't have any 3t component, right? So of course because of that this is going to be 0, right? This is going to be 0, and so on. So now, with that said, I have a question for you. Say I have a signal xt, okay, this is an unknown signal, okay, so xt is an unknown signal, right? And if I tell you this, unknown signal, again periodic signal, we are already only discussing periodic signal. Okay, if I tell you this, it's xt is an unknown periodic signal, and I know I somehow can multiply xt with sine t and integrate it from minus pi to pi and divide it by pi, and somehow I figured out that the result is 3, right? So I know xt is an unknown signal, but somehow I managed to multiply the signal with sine t and integrate it from minus pi to pi and divide the result with pi, and somehow I got a result of 3. If I tell you that, what can you tell me about the signal? So question is then, yes, so even though xt is an unknown signal, we can, from this integration, from this result of this integration, we can infer that xt has a component that looks like this. So this is not the only component in xt. So I cannot say xt is equal to this, because it would or could have something else, right? But this is one of the components I can say for sure. So if xt is an unknown signal, I can carry out this integration on, okay, and if I see the result is 3, then I can say that xt has a sinusoidal component of frequency 1 hertz, 1 radian per second, right? And this is the signal, right? This is the component, right? So I can say yes. So xt must have a component like this. It might have something else, I don't really know. Right? But again, now say we additionally know that this integration minus pi to pi is 0, right? Somehow we carried out this integration and we got some additional information on xt, and this is the additional information we have. Now if we have this information in addition to the previous information, what can I now say? I can now say xt right? So there must not be a sine 2t, right? Because of this 0, I understand that there cannot be a component of sine 2t, right? Because if there were a component of sine 2t, right? This integration would not be there, 0 would not become could not have become 0, right? So are all of you following what I am trying to say here, right? So with that said, let's say we have some other additional information. Let's say we also did this integration, and the result is say -1. So what can I now say about xt? So of course from this information we can say xt has a component of sine 3t with an amplitude of -1. So previously I knew, so we can say xt has -1 sine 3t. So this is one of the components of xt, right? So therefore in total xt has a component of sine t, okay, and which had an amplitude of 3, we did previously. It did not have any component of sine 2t, and it has a component of and something else, right? So this is something we discovered earlier, okay. By doing some other integration, and again, and for this we just discovered, right? I think this is understood, right? Right. So by now I think you can understand that we can carry on such integrations on a signal, and we can do something interesting things about it. So let me show you a few examples that would actually enforce this idea here. So all right, so look at this one, okay. So these are simple demos I made using Python for you to understand. So this blue line here, this blue one here, is representative of this signal, which is sine t, and this yellow one here is 1 by pi sine 1t, so sine t again, and this one here is the product of them. So the figure down below is the product of them. So this is multiplication of ft or xt, whatever you want to call it, with sine t, okay, this one. So these two signals, okay, and we are integrating from -pi to pi. So if I do the integration from -pi to pi, it will simply be the area under this curve, right? And we have divided the area by pi. So this is the integration. So basically, so whatever we are doing, so so this is what we are doing so far, right? So we have this signal, right? So this is again sine t, and this is again 1 by pi sine t, and we have just multiplied them, and this is the and divided by 1 by pi. So of course this integration is going to be 1, right? That's quite understood because of our mathematical development so far. We understand that this integration is going to be 1. And the area here also agrees to our concept here. We can see the entire area is positive, And if we can calculate the area, we will see that the area under the curve is indeed equal to 1. So yes, so I can now say this ft actually has a sinusoidal component of 1 radian per second frequency and has an amplitude of 1, right? So we can say that. So with that said, if I proceed further, now look carefully what I just did. So this blue one is again sin t. This blue one is again sin t, and we now multiplied this blue one sin t, which is the signal. The signal is sin t. We are now multiplying that with sin 2t, 1 by pi sin 2t. So this yellow one is 1 by pi sin 2t. Okay, and we are actually trying to see this integration, 1 by pi integration from minus pi to pi on the signal into sin 2t dt. And of course, since the signal is sin t, you know that the integration is going to be 0. But look at these areas. Okay, this is the total area, right, under the curve. So that's the integration, right? But you can very clearly see that these ones, the blue ones, are positive areas. These positive areas are being equally cancelled out by the negative areas, right? So the total area is actually 0 under this integration. So if I multiply this blue one, the signal, okay, which has only a 1 radian per second sinusoidal component in it, with a sinusoid of 2 radian per second frequency, and multiply them and calculate the area under the curve, we will see that the area under the curve is actually 0, because the positive areas are actually equally cancelling out the negative areas. So the integration is 0. And of course, from our mathematics, we already know that since this does not have any sin 2t component, so it does not have any 2 radian per second sinusoidal component, the result is actually 0. The resulting area is 0, right? So this is again simple to understand. Again, yet another example. Original signal, the signal itself has only 1 radian per second sinusoidal component, and we are multiplying that with a 3 radian per second sinusoid, okay, and calculating the area. Of course, the area is going to be 0. And here the cancellation of area is not quite evident, but you can calculate it mathematically, and you will see that these positive areas will be cancelling out the negative areas. So these two positive areas, positive lobes, are cancelling out this area. These two positive lobes are cancelling out this area, right? So something that you can actually grasp from this. Now again, say we have kind of a more compound signal, right? Say we have a signal which is comprising of sin t and half sin 2t. So it has a 1 radian per second component with an amplitude of 1, and a 2 radian per second component with an amplitude of half. So 1 radian per second component with an amplitude of 1, and a 2 radian per second component with an amplitude of half, right? So if I want to find out what is the magnitude, what is the amplitude of the 1 radian per second component, what am I going to do? I am going to multiply the signal with a sinusoid of 1 radian per second frequency, okay, and calculate this area. And of course, this area is going to be equal to 1. That is the result here. Similarly, if I want to see what is the amplitude of the 2 radian per second component in this signal, what do I have to do? I have to take this signal, multiply this signal with a sinusoid of 2 radian per second frequency, integrate it from minus pi to pi, divide it by pi, and of course the result is going to be 0.5. And again, as you can see, these are the positive areas and the negative areas are slightly smaller. So when you add them up, you will get a half. Right? So this is again, I think, understood, right? Similarly, I have this signal. Okay, so this again, the same signal that has a 1 radian per second component of amplitude 1 and a 2 radian per second component of amplitude half, and we are trying to see what is the amplitude of the 3 radian per second component in it. And of course, it does not have a 3 radian per second component in it. So again, if you calculate the total area, you will see that the result is 0, right? In a similar fashion, say now we have a signal, slightly more composite signal. This signal has 3 components in it: a 1 radian per second component with an amplitude of 1, a 2 radian per second component with an amplitude of half and a 3 radian per second component with an amplitude of 2. And I want to see what is the amplitude of the 3 radian per second component in it. How do I get that? I simply multiply the signal with sine of 3t, so which is basically a sinusoid of 3 radian per second frequency, and do the integration from minus pi to pi and divide everything by pi, and the result I get would be the amplitude of the 3 radian per second sinusoidal component. And again we will see that the area is actually equal to 2, which is the amplitude of the 3 radian per second sinusoidal component here. Similarly, in the previous example, if the amplitude of the 3 radian per second sinusoidal component was minus 2 instead, okay, the result of this integration would be minus 2. As you can see, the negative areas are dominating the positive areas here. So that way, the total area, if you calculate it, you will see that the result is minus 2. Again, this is indicative of the fact that this signal comprises, or at least has a component of 3 radian per second frequency that has an amplitude of minus 2. In a similar fashion, say again I have a signal which does not have any 2 radian per second component, only has a 1 radian per second component and a 3 radian per second component. Okay, so this signal has a 1 radian per second component of an amplitude 1 and a 3 radian per second component of an amplitude 0.33, and I want to see what is the amplitude of the 2 radian per second component. So what do? I multiply the signal with a 2 radian per second sinusoid and integrate it from minus pi to pi and divide everything by pi. The result will give me the amplitude of the 2 radian per second sinusoidal component. Of course, that result is going to be 0. As you can see, the positive areas here are cancelling out the negative areas. Right? In a similar way, the same thing happens here. We have this same signal sin t plus sine 0.33 sine 3t. So this signal does not have any 2 radian per second component, but it has a 3 radian per second component. So if I want to see what is the amplitude of the 3 radian per second component, what do I have to do? I have to multiply the signal with a sinusoid of 3 radian per second, do the integration from minus pi to pi, divide everything by pi, and the area under the curve will give me the amplitude of the 3 radian per second sinusoidal component. Again, as you can see, the area is 0.33. You can actually calculate this mathematically. But understanding this is the important part. Have a feeling of this is the important part, right? So I believe all of you could follow this. So let me go back. Right? So now with this, so my point is this: imagine we have a signal that looks like this. So please let me know if all of you could follow what I just demoed here. Please let me know. Now imagine. So please let me know if all of you could follow what I just showed you. Then we shall proceed. Right. So where are the others? Only Shamomai says he understood. Where are the others? Please let me know if you understood this. So imagine, thank you. So imagine we have a signal xt which kind of looks like this, has a sine 1 radian per second component, has a 2 radian per second component, has a 3 radian per second component, has a 4 radian per second component, has a 5 radian per second component, and so on, has a n radian per second component, and so on, right? Right. Imagine a signal that has many sinusoidal components like that, right? Right. And if I know that somehow, if I somehow know that this signal can be expressed as a sum of different sinusoids of different frequencies, right? If I know something like that, right? With this knowledge, my question is, can I calculate the amplitude that appears here? So if the amplitude how do I figure out what is the amplitude of the 1 radian per second component? How do I do that? I simply calculate that by doing this integration from minus pi to pi. If I take this signal and multiply this with sine t, right, and do the integration and divide everything by pi, okay, and if I get something like, say, b1, okay, I can happily say that b1 is the amplitude of the 1 radian per second sinusoidal component, right? In a very similar fashion, if I multiply the signal with sine 2t and do the same integration and I get a result of b2, then I can say this signal has a 2 radian per second sinusoidal component that has an amplitude of b2. And in a similar fashion, in a similar way, if I multiply the signal with sine 3t and do the same integration, and if I see that the result is b3, then I can happily say that this signal has a 3 radian per second sinusoidal component that has an amplitude of b3, right? And so on. So if I say again multiply the signal with sine 4t, okay, and do the same integration, and if I get something like a b4, okay, I can say this and this. So as a matter of fact, if I multiply the signal with sine nt, what do I really get? If I multiply the signal with sine nt and integrate it from minus pi to pi divided by pi, so what I get is b1. What is this? This is the coefficient of the n radian per second sinusoidal component, right? So if I multiply the signal with sine nt and integrate it from minus pi to pi, divide everything by pi, the result I get is nothing but the coefficient of the n radian per second sinusoidal component present in the signal. So again, my assumption is that I have a signal that is expressible in this way, that can be expressed in this manner. And if it can be expressed in this manner, then if I multiply the signal with sine nt and do the integration from minus pi to pi, divide everything by pi, Okay, the result gives me the coefficient of the n radian per second sinusoidal component. Of course, understandably, we just discussed that n can be equal to 1, 2, 3, or basically anything, right? So mathematically speaking, n is just any natural number, right? It can be 1, 2, 3, 4, 5, 6, and so on, right? All the natural numbers. So if I multiply the signal with sine 1t and integrate, do the integration, I get the coefficient of the 1 radian per second sinusoidal component. If I multiply the signal with sine 2t and do this integration, I get the coefficient of the 2 radian per sinusoidal component, and so on, right? I believe all of you got that and got up to that point, right? Right. So please let me know if you cannot follow this, and please let me know if you can follow this. So can you follow this again? Please let me know. Right, good. So now let me ask you a question. Similar thing, kind of similar thing, like this. Uh, Again, we started our discussion today with an integration. Okay, let's do another one. Right now, let's do this integration. Okay. Okay, I am not asking you to do the integration, but you can try it at home, and you will see that it has a very similar result. Okay, you will see that this is again 0. Okay, if m is not equal to n, and this is again 1 if m is equal to n, and again m and n are both natural numbers. It's a very similar result. We did the same result with sine, right? Yeah, it's exactly the same thing, but you can try that at home and let me know that if you cannot derive this, right? So we have another expression. So instead of saying it, yeah, right, so we have another expression, right? So I would encourage you to try this at home. Okay, and we also have something like this integration. So we have so far seen that integration of sine mt into sine nt dt from minus pi to pi divided by pi has got this kind of a result. Again, integration from minus pi to pi on cos mt and cos mt into cos nt dt has got a similar result like this. But if I mix and match sine and cos, so if I write something like sine mt cos nt dt, this would be actually equal to this sine nt cos mt dt, because you can calculate this and verify for a fact that this is actually 0. So if you mix and match, the result is actually 0 always. This is always 0. So we basically have 3 formula for us with us. Okay, one with sines, one with cosines, and one with sine cosine mixed, right? Yeah, so this is 0 for all of them. You can actually verify this as a fact, right? So with that said, now let me ask you a few simple questions once more. Okay, so what is this integration? So I'm writing a few integrations, and please let me know if you can follow them. So I can say this is 0, integration from minus pi to pi, 1 by pi, that's equal to 1. Right, and so on. We have very simple examples, right? So with this in mind, let's go back and look at this one. So if I have a signal that is considered to be comprising of sinusoids, okay, of different frequencies like sine of 1 radian per second, 2 radian per second, 3 radian per second, and so on, and with amplitudes b1, b2, b3, b4, and so on up to bn for n radian per second, then the component, the amplitude of the n radian per second component can be calculated by this integration. So if I put n equal to 1, I get the component for amplitude for the 1 radian per second component. With that idea, we can now say the idea is, if xt now looks like this, it has a cosine component of 1 radian per second, and a cosine component of 2 radian per second, and a cosine component of 3 radian per second, and so on, and a cosine component of n radian per second, and so on. If it has something like this, then what can I do? I can do this integration, right? I can take the signal, multiply it with cosine t, integrate it from minus pi to pi, and divide everything by pi, like this one, right? Divide everything by pi, and I would get the component, the coefficient of the 1 radian per second cosine component, right? So if this is equal to b1, so if this is equal to a1, then I can say we have an a1 here, right? Similarly, if I multiply this signal with cosine 2t, cos 2t, and do the integration, and if I get something like a2, so we can say the amplitude of the 2 radian per second cosinusoidal component is a2, right? Similarly, if I multiply the signal with cos 3t, right? Right? So we can have that. Similarly, in order to find out the amplitude of the n radian per second cosinusoidal component, we can simply multiply the signal with cosine nt, right? And the result I get would be the coefficient of the n radian per second cosinusoidal component. Again, n here is from 1, 2, 3, and so on, right? That is, n belongs to the set of natural numbers, right? So please let me know if you can follow. right? Right. So let me proceed with this. Now say I have a signal xt, okay, like this, like a1 cos t plus a2 cos 2t and so on plus an and so on, right? And so on. So if I have something like this, right? If I have a signal that is representable this way, right? This is a1 cos t, a2 cos 2t, a3 cos 3t, something like that. This can be actually very nicely written as in the form of a summation, right? All of you actually know that. So we have a summation from n equal to 1 to infinity on an cos nt, right? So this, a signal that is kind of representable this way, okay, can be written as this, right? So it's like a1 cos 1t, a2 cos 2t, a3 cos 3t and so on, right? So alongside cosinusoidal component, if the signal also has sinusoidal component like b1 sin t plus b2 sin 2t and so on, then that can be appended like here. For example, this is going to be bn sin nt, right? Right? So I think this is understood. Then all these coefficients a1, a2, a3, etc., right, can be calculated simply as integration 1 by pi, integration from minus pi to pi, xt cos nt dt, where n varies from 1 to 3 and so on, right? We just discovered that, right? Already we established that, right? So again, bn, all the coefficients of the sinusoidal components can be expressed this way. Right? So these are the coefficients of the sinusoidal components. Right? Right. So now, many years back, Joseph Fourier discovered this. Said this, okay, if I have a signal or a function that satisfies these three conditions, so if a periodic signal with a fundamental period of 2 pi. Yes, that is my and that is my entire point, because if I just tell you the formula and ask you to solve something, okay, using your mathematical aptitude you will be able to solve it, right? But you will never understand where things came from, right? So understanding the background behind this is more important than actually solving the problems, in my in my opinion. And sooner or later you will actually come to that realization. If you blindly mug up some formula, it doesn't contribute to your knowledge. So if a periodic signal with a fundamental period of 2 pi, okay, satisfies, again we shall have 5 total classes on Fourier analysis, so this is the first class on that. We shall discuss plenty of other things, so don't worry. We shall solve quite a few problems, and so let's see that. So if a periodic signal with a fundamental period of 2 pi satisfies these 3 conditions. So what are the conditions? Condition number 1, so again we shall actually discuss these conditions later on, okay, at a later class, but for now just try to remember the conditions, right? Okay. So the conditions are this. The number 1 condition is that the periodic signal, the signal has only finite number of finite discontinuities. So the signal only has finite number of finite discontinuity. So that's the condition number 1. We shall later on discuss what are the meaning of right. Actually, to be frank with you, actually I wanted to study mathematics, okay, and no one let me do that anyway, so don't worry. So the signal has only finite number of finite discontinuities. This is one of the conditions that signal must satisfy. The other condition is that the signal only has a finite number of local extremas in any just forget that. Finite number of local extremas. What are extremas? Maximas, minimas. Right? So let me just I just said okay, right. So Fourier said, not exactly Fourier said, but later on discovered that if a signal satisfies these 3 conditions, if a signal satisfies these 3 conditions, for example, the signal has finite number of finite discontinuities, and again we shall learn what are the significance of these conditions, but for now just try to understand. If a signal is bounded, has finite number of finite discontinuities, so that signal actually does not go to infinity, okay, and does not have infinite discontinuities like tan t, for example. If I have a signal tan t that has infinite discontinuities, those kind of signals are not valid here, okay. And signal only has finite number of local extremas, so it cannot have infinite number of maximas and minimas. If these 3 conditions are satisfied, Okay, these three conditions are actually they do have a name. These conditions are known as Dirichlet condition. Named after a mathematician named called Gustav Dirichlet, and Gustav Dirichlet actually discovered these conditions, that if these three conditions satisfied, then the signal is expressible as a sum of sinusoids like this. Right. Only with one subtle difference. So a signal has to satisfy these conditions, and then the signal is expressible like this, right? Only with a subtle difference that the signal will also could also have a constant value, right? Right? That's called a DC component. So the signal could have a DC component added to this, right? So that's the idea, right? So we shall solve a problem shortly, so we shall learn that. But how do I calculate the DC component? So what about the DC component? How do I calculate the DC component in any signal? What is the DC component? DC component is known as the average value, right? So how do I calculate the average value of this? We just have to average it. How do I average it? Integrate it over a certain period of time and divide it by that amount of time. So I integrate it, right? I simply integrate the signal over a certain period of time. What is the period of time? From minus pi to pi, and divide it with the total amount of time, which is 2 pi here, and that gives me the DC component. So this is the DC component of the signal, right? Right? This is understood, right? So that's the DC component. But recall that moments ago we said that an, which is the cosinusoidal component, kind of has this expression, right? 1 by pi from minus pi to pi xt cos nt dt, right? So with this expression, if I manage to put n equal to 0, what do I get? I get a0, which is 1 by pi integration from minus pi to pi xt, and cos 0, which is cos 0, that's 1, right? dt, right? Now compare these two expressions. Now compare the value of the DC component and a0. We can quickly realize that the DC component is nothing but a0 by 2, right? Right? So oftentimes we express the Fourier series like this. Where the signal satisfies all the three Dirichlet conditions, and the sinusoidal components, it has sinusoidal components, cosinusoidal components, because of that particular scenario, because it satisfies all the Dirichlet conditions. It has sinusoidal components with amplitudes bn for the n radian per second sinusoidal component. It has cosinusoidal components, which for the n radian per second cosinusoidal component, the amplitude is an, and it has a constant value. It has a constant component, which is the DC component. Then all these components can be separately calculated as this. That's the DC component, or corresponding to the DC component. That's the cosinusoidal component. And that's the, okay, I don't have any space right now. Hold on. And that's the sinusoidal component. Right. So that's our expression for Fourier series. So you have seen this expression, but you probably never knew where it came from. But now we have actually seen that. Right. Right. So let's end our discussion today. So it will be like 20 more minutes. 20. We hope so. Let's solve pretty popular problem. Right. So I think you got the point, right? Let's solve a popular problem. How popular? Very popular. Say we have a signal that looks like this. If you have any questions so far, please let me know. So this is the pulse, right? Rectangular pulse or square pulse, whatever you want to call it, right? It's often known as a square wave, even though it might be a rectangular wave. Anyway, does not matter. So it's a pulse for all intents and purposes, right? So let me change it to extend. Right. So that's the waveform, right? Again, the important parts are, first of all, before we can even discuss Fourier series of a signal, you have to first understand, first figure out what is the period of the signal, right? Question is this signal periodic? The answer is yes, the signal is periodic. So the first point you need to figure out the periodicities of the signal, right? So it is periodic. Okay, and what is the period? Is 2 pi, right? So again, just to be very clear, today we have discussed Fourier series for signals that are periodic with a period of 2 pi. But again, by virtue of the discussion we had in the last to last class, where we studied signal operations like time expansion, time contraction, from those discussions we can understand we can very easily change the period of a signal by doing a time expansion or time contraction, right? So if instead of the period being 2 pi, if the period is something else, it does not really matter at all. We can just do a time contraction or time expansion on the signal and we will get the results. We shall solve problems like that later on. So it's a periodic signal. So first of all, now we have to see if all the three Dirichlet conditions are satisfied or not. So what is the first Dirichlet condition? So what is the first Dirichlet condition? So what is the first Dirichlet condition? The signal has finite discontinuities, finite number of finite discontinuities. Yes, the signal actually has discontinuities in this regard. So as you can see, this signal has discontinuity here. So at time t equal to 0, this signal actually has a discontinuity, right? It abruptly jumps from -1 to 1, right? And again at pi, this signal once again has an abrupt discontinuity, right? Jump discontinuity, and it jumps from +1 to -1. And again at 2 pi it has a jump discontinuity. At -pi it has a jump discontinuity. At -2 pi it has again a jump discontinuity, right? But these jump discontinuities are finite discontinuities, right? So Dirichlet condition 1 has been satisfied. So what about Dirichlet condition 2? Dirichlet condition 2 says that it only can have finite number of maximas or minimas, right? Finite number of extremas. As you can see, it only has finite number of extremas, right? You can always count the number of extremas, minimas, for example, maximas, minimas, right? So again, that condition is satisfied. Again, if you have any question, please ask me. And the signal is bounded, right? It is not going to infinity. So all the three Dirichlet conditions are satisfied. So again, before I can actually go further, I have to tell you that the Dirichlet conditions are known as something called the sufficient conditions. And by virtue of that, what I mean by sufficient condition is that if a signal is periodic and it satisfies the Dirichlet conditions, it would always have a Fourier series expression, right? But this is a sufficient condition, which means a signal can have a Fourier series expression even though it does not entirely satisfy the Dirichlet conditions, right? That's what a sufficient condition is, right? So Dirichlet conditions are sufficient conditions, which means if the signal satisfies Dirichlet conditions, it will definitely have a Fourier series expression, right? But in order to have a Fourier series expression, okay, it is not necessary. So Dirichlet conditions are not necessary, but sufficient. If Dirichlet conditions are satisfied, the signal will have a Fourier series expression, definitely. But a signal can have a Fourier series expression even though it does not fully satisfy the Dirichlet conditions. So this is something you have to keep in mind. So with that said, we have to find out an expression for the signal within the period. So for example, from -pi to pi, what is the expression for the signal? So we have a very simple expression for the signal. What is the expression for the signal? Very simple. So I can say xt. Again, this is the piecewise definition. So that signal has a value of -1 and +1. This signal has a value of -1 when it is between -pi and 0. So when time is between -pi and 0, and it has a value of 1 when time is between pi. Hold on. Say, right? I do not really care about the equal to signs, right? So imagine this is the condition, right? Something like that. So I can say something like this. That's sufficient for us, right? because discontinuities are allowed here. Right. So so this is again a periodic waveform that has that is periodic with a period of 2 pi. Right. So every 2 pi seconds it repeats itself. Right. So now we have that previous scenario where I know about the signal, but I also know about the fact that this signal is expressible in this form. This could have a DC component, and then this could have sinusoidal components and cosinusoidal components. Okay, sinusoidal components that are cosinusoidal components that are expressed in this form, and sinusoidal components that are expressed in this form. But I don't really know the coefficients, right? I don't really know the value of A1, A2, A3, A0, B1, B2, B3, etc. Right? I don't really know the values. Yeah. So I am trying to calculate the values, right? So let's start with A0. What is the DC component of this signal? You electrical engineers, you already know that this signal has zero DC bias, right? This signal has zero DC component, because if you average the signal over time, the average value will be zero, right? So this signal has a DC component of 0. But we can see that by integration, right? So how do I calculate the DC component? By simply doing this integration. By calculating A0, which corresponds to the DC component, and we are doing xt dt. And again, this integration can be split into two portions. For example, one from minus pi to 0 and another from 0 to pi. Okay, so while the signal is from minus pi to 0, the value is -1. So I have -1 dt. And while the signal is between 0 and pi, the value is 1. Right? So this is 1 dt, right? So understandably, what is the integration here? So I have 1 by pi. So if you do the integration here, so I would have minus t from minus pi to 0 and a plus t from 0 to pi. So I would have a 1 by pi, and I would have a 0 minus pi plus pi minus 0. So if you calculate this, why did it go wrong? Wait a second. Oh, sorry, 0 plus pi, huh? 0 minus of minus pi. So the answer is actually 0. So the DC component is A0 by 2. That's actually 0. We just cleared that up, right? So for this signal, the DC component is 0. So we understood that. Right. So now let's calculate the coefficients of the cosinusoids, right? So which are a, n. So we're calculating a1, a2, a3, etc., which are respectively the coefficients for the 1 radian per second, 2 radian per second, 3 radian per second cosinusoids, right? So how do I calculate that? I do this integration. So I basically multiply the signal with cosinusoids of different frequencies, and particularly I'll get those particular frequencies, right? Coefficients of those particular frequencies. So if when n is equal to 1, it gives me the coefficient of the 1 radian per second cosinusoid implicit within the signal, right? And so on. So I'm doing this integration, but now again, like the previous one, I have to split this integration into two portions. One would be from minus pi to 0 with xt cos nt dt. Another would be from 0 to pi xt cos nt dt. So with that said, this integration is minus this, and of course within those limits. And again, if you have any question, please interrupt me and ask me a question. Cos nt dt plus integration 0 to pi 1 cos nt dt right. So again, what is the integration here? There will be minus because of the minus sign, and I will have a sin nt by n from minus pi to 0, and have a plus sin nt by n from 0 to pi, right? So I would have, so I'm taking 1 by n outside. Let's do that later on. So when I put 0, of course sine 0 is 0, and when I put pi, again I have the same thing we discussed a few moments ago, right? If I put pi, we have a integer multiple of pi inside a sine, right? That's a 0. Similarly, if I put the lower limit here, that's also a 0. If I put the upper limit, which is again an integer multiple of pi, that also gives me a 0. So overall, this is just a 0, right? So this is 0, right? Without any confusion. So actually, this is 0. This is also 0, right? There is no confusion about that. So far we have realized that for this signal, okay, for this particular signal, this turns out to be 0. This signal does not have any DC component, and this also turns out to be 0. So it appears this signal does not also have any cosinusoidal component, right? So let's look at this one. This signal must have these components, right? Otherwise our entire idea is wrong, right? Right. So let's calculate the coefficients of the sinusoidal components, so which are represented with Bn. Again, B1 is the one coefficient of the 1 radian per second component. Similarly, B2 is the coefficient or the amplitude of the 2 radian per second sinusoidal component, and so on. So this is going to be 1 by pi integration from minus pi to pi, again xt sin nt dt right. So again, we have to unfortunately or fortunately enough, we have to split this into two parts. Again, when the signal is between minus pi and 0, I have a minus 1, right? So I'm just skipping one step here, and from 0 to pi we have plus 1 here. Sorry, it is not sin t, it is sine of nt. Right. So again, now, so if I do this integration, I have minus, and integration of sine nt, all of you know that it's minus cos nt divided by n. So this minus sign actually cancels out. No, your answer is not correct entirely. Okay, for here the integration becomes minus, so minus sign cancels out, cos nt by n. And here in this case, in the next one, of course, we have again a minus sign outside, because of course this is minus cos nt by n. That's simple school level integration, right? That's fine, right? You will see that the answer is not that simple. We will see, right? because we have an n here, right? We have to deal with that. Okay, right. So let's put 0, right? If I put the upper limit 0, what do I get? Cos 0 is always 1, right? So instead, let's do something useful. Let's bring the n, which is in the denominator of everything, outside. So outside I have a n pi, right? And let's deal with the cosinusoids inside. So if I put the upper limit here, what is the upper limit here? Okay, 0, right? So what is cos 0? That's universally 1, right? No issues. But what if I put minus pi? So I would have minus. So I put minus and lower limit. I am putting so minus n pi. So that's the thing. And then we have the upper limit. Yes, it appears that Shambha's answer is correct. Let's see. So if I put the upper limit here, I have cos n pi, and again the lower limit is 0, so cos 0, which is 1. Right. I think putting the limits isn't an issue, right? But try to understand that if I now expand everything, I have 1 minus cos of, now again cos of minus theta is simply cos theta, right? So this is n pi, right? And I have minus cos n pi and plus 1. So what do I have? I have 1 by n pi and 1 plus 1, 2, minus cos n pi minus cos n pi, so 2 cos n pi, right? Right? So I have 2 by n pi, 1 minus cos n pi. Now unlike sin n pi is always 0 as long as n is an integer. Cos n pi is not like that, right? Right? So cos 0 is 1, cos pi is minus 1, cos 2 pi is 0, right? So and so on and so forth, right? So similarly cos 3 pi is plus 1, sorry, minus 1 and plus 1 and so on. So let me clear this up. So again, instead of doing that, we have a simpler way of doing this, right? I hope you would understand. So this is n pi. So of course this is 1 minus cos theta, right? So 1 minus, OB is partially correct with his answer. So 1 minus cos theta is half is 2 sine square theta by 2, right? Your school level formula, right? Right. Let's apply that here. So I have 2 sine square n pi by 2. I don't think there is any issue with this, right? So I have 4 by n pi sine square n pi by 2, right? No problem, right? So that's the expression for our Bn. So therefore Bn is 4 by n pi sine square n pi by 2. So what does it tell you? What is this? Again, let's go back. Okay, we could express our signal as this a0 by 2, which is corresponding to the DC component, and a summation of sinusoids that has cosinusoidal components and sinusoidal components expressed as an cos nt plus bn sin nt, right? But we figured out for this particular example, this is 0, these portions are also 0, only these portions do exist, right? And for these portions, for the sinusoidal components, particularly these sine components, particularly for these sinusoidal components, so these represent the coefficients, right? So what is B1? So what is B1? So b1 is the coefficient of the 1 radian per second sinusoidal component, right? So the fundamental sinusoidal component, 1 radian per second means it has a period of 2 pi. Yes, now B is correct. No, you are still slightly incorrect. Let's see. We'll do that. So B1 is the coefficient of the 1 radian per second sinusoidal component, right? So 2 pi period, right? The fundamental component, right? So with that said, what is B1? Again, let's go back to the expression. This is the expression, right? So 4 n pi. So I'm putting 1. So 4 by pi. So n is equal to 1, and I have sine square n is equal to 1 here, right? Sine square pi by 2. What is sine square pi by 2? That's 1, right? So I have 4 by pi, right? I think that's understood, right? Similarly, what is B2? B2 is 4 by 2 pi. Now I have sine square 2 into pi by 2. That's n, right? Now what is sine 2 into sine square 2 pi by 2? What is this? That's sine square pi. What is sine square pi? 0, because sine pi is 0. So this is 0, right? Similarly, B3, what is that? 4 by 2 pi, right? 4 by 2 pi, very sorry. So 4 by 3 pi. 4 by 3 pi, I have sine square 3 pi by 2, right? What is that? Sine square 3 pi by 2. So what is sine 3 pi by 2? That's 1. So what is sine square 3 pi by 2? So that's why if I square this up and subsequently I have 4 by, so it's 1, right? 4 by 3 pi. Similarly, if I have B4, I have 4 by 4 pi. I have sine square 4 pi by 2. That's 2 pi. Again, now a multiple of pi. So it's 0, right? Similarly, if I have B5, which is 4 pi by 5, 4 by 5 pi, sine square 5 pi by 2. Again, this is 1, so I have 4 by 5 pi. I think you can follow a pattern from this. You can figure out a pattern from this. I would be able to say that from this, Bn is let's forget that. Let's forget that, because that will be slightly more complicated to write. Okay, let's forget that. So what is B1 again? What is B1? It's the coefficient of the 1 radian per second sinusoid. What is B2? Coefficient of the 2 radian per second sinusoid. B3, coefficient of the 3 radian per second sinusoid. B4, coefficient of the 4 radian per second sinusoid. B5, coefficient of the 5 radian per second sinusoid. So the signal we have, okay, again the general expression is this, but we don't have any DC component, we don't have any cosinusoidal component. For this particular example, we only have sinusoidal component. This signal is simply like a summation Bn sin nt from n equal to 1 to infinity. For this particular scenario, this is like B1 sin t plus B2 sin 2t plus B3 sin 3t plus B4 sin 4t plus B5 sin 5t and so on. And we just calculated the value of B1, B2, B3, B4, B5, etc. Right? So with our example, this is going to be 4 by pi. And what is the value of B1? We are writing the B1, right? So 4 by pi, right? So I have 4 by pi sin t. What is the value of B2? It's 0. What is the value of B3? It's 4 by 3 pi. So I have 4 by 3 pi sin 3t. Similarly, what is the value of B4? It's 0. What is the value of B5? It's 4 by 5 pi sin 5t and so on, right? And so on. So I can now happily take 4 by pi common outside, and I would have sine t plus 1 by 3 sine 2t, sine 3t plus 1 by 5 sine 5t, and I think you can guess the next would have been 1 by 7, something like this, 1 by 7 sine 7t, and so on. So this signal is actually comprising of only odd multiples of odd frequencies of sinusoids, right? Odd multiples of the fundamental frequency, right? Odd harmonics, right? So this is the fundamental sinusoid within that signal, which is sine t, 1 radian per second frequency. Now we have another component of 3 radian per second, another component of 5 radian per second, and so on, right? So this is how you can actually express the original signal. So what was our original signal? So you can, if I go back, this is the signal we actually were discussing. Right? So this is the signal we have been discussing, and for this signal we can express this in this way. So of course we can kind of what should I say, compactify this expression and kind of write something like this. So we have 4 by pi summation n equal to 1 to infinity. So I'm just trying to express this, right, in a slightly compact form. So I have sine of 2n minus 1 t divided by 2n minus 1. So these are all odd numbers, right? So I have 4 by pi, it's a summation, right? N starts from 1 to infinity, and now we have sine. So when n is 1, this is sine t by 1. When n is 2, it's sine t by 1 plus sine 3t by 3. Okay. When n is 3, it's sine t by 1 plus sine 3t by 3 plus sine 5t by 5, and so on, right? So this is nothing but this expression. So this signal can be actually expressed in this form, right? So please let me know if this is fine for you, because we are just quickly jump into a demo and end today's discussion. So please let me know if you can actually follow this. Please let me know in the live chat. So please let me know in the live chat if all of you could follow this. Right, so let's jump into our demo. Okay, right. So now we have just this expression, the expression that we just did moments ago. We have that expression. Right? Oh, we have to have a 4 by 5. Right, so this is something we just okay, you have a question, right? Would we find amplitude of some specific component with the help of an op-amp to perform that? Yes, actually, yes. The question is, someone asked that can we actually do this integration using a hardware? Absolutely, we can actually. Okay, all this analog computation can actually be done using op-amps, right? And in today's digital era, we can do everything digitally, of course, right? We have something called a discrete Fourier transform or fast Fourier transform. And I might have told you earlier that actually anytime you are actually seeing a video, listening to an audio, it's compressed. Okay, you already know that, right? We do not have infinite bandwidth. We cannot send everything we actually have, right? We have to compress. And most of the compression algorithms that we have for audio and video, they do employ something called a discrete Fourier transform, specifically something called a discrete cosine transform. Okay, so yes, actually we can do all this computation very easily. Okay, right. So again, anytime you are actually looking at a spectrum of a signal, we are doing a Fourier transform. We shall discuss all those things in our discussion on Fourier transform later on. Okay, right. So again, now we have look at this signal. So this blue one is representative of the pure square pulse, right? It's a pure square pulse. For example, we have a discontinuity from this point, we have a discontinuity here, and so on, right? And this is the fundamental frequency. This is the fundamental sinusoid. This is sine t. This is 4 by pi sine t, right? This is the first part, right? Now, if I add this, right? Let me right. All right. So this is the fundamental frequency, right? So if I increase the frequency, so I have two components, right? Now I have sine t and I have 1 by 3 sine 3t. So I have added them. So this is the sum, right? So now we have another component, right? So now I have sine t plus sine 3t, 1 by 3 sine 3t plus 1 by 5 sine 5t, and this orange one is representative of that. So I have another component. So I have added 1 by 7 sine 70. I have added 1 by 9 sine 90. 1 by 11 sine 11t. I have added to that. So and so on. If I keep on adding these sinusoids, what do you see? Don't you see that this expression, okay, which is representative of the Fourier series, okay, kind of automatically merges into that. So if I actually put even a higher value, so that I can actually go even further, okay, you'd see if I go even further, see, right? So this is a low one, right? Only one component, two. So and we are adding how many components we are going to see. So right. So as I keep on adding the high frequency components, what do I see? I see that the Fourier series actually for the signal, it merges with the original sinusoid. Do you have any question with this? So if I keep on adding sinusoids, so as you can see, the expression becomes right. Let it calculate. Yeah, it more or less represents the square pulse, right? But one thing to note though, okay, in this regard, you should note one point, one very important point, okay. The Fourier series or the expression for Fourier series, okay, only ensures convergence of the Fourier series, okay, or convergence of the Fourier series on the points for the original signal where it is continuous, right? So what do I mean by that? I mean by that is the fact that look at the original signal, original square pulse. this original square pulse is discontinuous at t equal to 0. The point is, at this point, when t is equal to 0, the Fourier series will actually never converge with the signal. It will only go through the midpoint of the jump discontinuity. So what is the jump discontinuity? Jump discontinuity is from -1 to +1. So what is the midpoint of the jump discontinuity? It's 0, right? So the Fourier series ensures that at the point of discontinuities for the original signal, the Fourier series will go through the midpoint of the jump discontinuities. So even though I'm adding the signals, adding additional frequencies, look that the sum or the Fourier series sum, Fourier sum, actually going through the midpoint of the jump discontinuity. And whenever there is a discontinuity, there will be some ringing here. This is a ringing phenomena, right? As you can see, at this discontinuous point, the Fourier series actually diverges from the original signal. Okay, this divergence here, as you can see, the Fourier series actually diverges from the original signal at the point of discontinuity. This is known as something called the Gibbs phenomena. We shall discuss about this at a later class. So in any case, try to understand that Fourier series only ensures convergence where the signal is continuous. Wherever the signal has finite discontinuities, of course, without finite discontinuity, the Fourier series is not entirely ensured. But wherever the signal has finite discontinuities, the Fourier series only converges to the midpoint of the finite discontinuity, not through the entire signal. And whenever there are discontinuities, there will be ringing like this. Okay, there will be certain jumps here, and those jumps, those ringings are known as the Gibbs phenomena, which we shall actually discuss later on in our signals and systems classes later on. In any case, that will be the end of today's discussion. Please let me know if you have any question. So I'll be here for 5 more minutes. Please let me know if you have any question. So I'm going to give you a homework. So and while I'm preparing the homework for you, just ask me any question you have. So we have this homework for you. Again, if anybody has any question. Right. So, okay, it took me a while to draw this. So this is the signal that you are supposed to do as a homework and figure out the Fourier series expression for this. So this is pi. This point is minus pi. This is a sawtooth expression, right? Sawtooth signal. This is 0. This is 2 pi. Again, this signal is periodic with a period of 2 pi, right? We shall discuss the convergence of Fourier series later on. Okay, we shall actually discuss the Dirichlet conditions later on while actually discussing Fourier transform. Okay, so your question for this homework problem is this. Okay. Right. So that will be your homework. So you are going to find out the Fourier series for this. In any case, if you don't have any questions, we're going to end our discussion today. We already took too long. Okay, I'll be waiting here for 5 more minutes. If you have any question, please ask. Again, thank you for joining. I'll let you know about the next class. And again, this video will be available after the stream, and I shall send you the handouts. Thank you very much. So if you don't have any more questions, we are going to end the discussion right now, and see you in the next class. Well, thank you. Stay home and stay safe.